All right, so on Wednesday we were talking about center of mass. And if I remember correctly, the last thing we did was we found the center of mass of this weird shape, yes?
Correct. Yes.
Okay. So it turns out there is another way you can do this. But I don't know that there's a ton of value in going through it. So, but just really quickly, here's the other way you can do this. So we did this by addition, right? We broke this thing up into 3 chunks, right? And found the center of mass of each of them, right? And then just used our particle equation to find the center of mass, right? The other way to do it is using sort of what I guess you would call subtraction. And basically what you do is you still break it up into parts, but instead, and this is a little bit weird, you treat, so you find the center of mass of, you know what, it'll take 2 seconds. Let's just do it. So here's how you do it by subtraction. All right, so here's what we're going to do. Instead of breaking it up into chunks and adding the pieces together, we're going to imagine it as 2 things. What's there and what's not there. Okay? So, let's pretend that hole wasn't there. Where would the center of mass of the whole thing be?
0.
So the whole thing, let's see, whole thing. Oops, that is not at all how you spell whole. Let's try that again. Whole thing. Like it. So, our center of mass would be at 0, right? And the mass of the whole thing, remember we just said that the area was proportional to the mass, right? So the area of the whole thing would be what? 36d, right? So 36 meters. So our mass would be 36 times, I think we were using capital M to represent the mass of one little block. Cool? Any problems there? All right, now, let's do the missing chunk. So the missing chunk, where would the center of mass for that missing chunk be? Let's see, I think it would be, well, you guys tell me. 2, right? Because d is 1 meter. All right, and then what would the mass of that missing chunk be? Well, the area is 2 times 2, so 4, right? Follow? All right, now, this is the weird part. Since that chunk is missing, I'm going to treat it as a negative mass, because it's mass that's not there. Follow? And then you just use the equation. So, the position of the center of mass should be the position of the whole thing times the mass of the whole thing, plus the position of the missing chunk times the mass of the missing chunk over the mass of the whole thing plus the mass of the missing chunk. So I'm still just using that same equation. The only difference is we've got a negative mass, right? All right, so let's see what we get. Oh, I gotta do this. Yeah.
For the missing chunk and the x is equal to 2m, can you just point that out for me?
Yep, I'm sorry. Yeah, thank you for asking if that wasn't clear. So what I'm looking at is this little bit here, right? Yeah. Okay, and its center, because that's symmetrical, the center of mass of it is going to be right at the center, right?
Yeah, all right.
And so this whole thing is 3, the block is 2, half of 2 is 1, so 1 plus 1.
All right, I got it.
Cool? Everybody good? I did not mean that to sound pandering. Are you good?
Yeah.
Okay. All right. Okay. So let's plug in our numbers. So let's see. The position of the whole thing is 0 times the mass of the whole thing is 36. Plus the position of the missing chunk is 2 times its mass is negative 4. Right?
Correct.
All over the mass of the whole thing, which is 36m. Plus the mass of the missing bit, which is negative 4m. So on the top, you're going to get negative, oops, I missed an m here. You're going to get negative 8m over 32m. Oh, it gives us negative 1/4 again, which is the same thing we got on Wednesday.
Whoa.
Cool?
Yeah.
So that's kind of a cool little trick. All right, problems? Yeah.
How do you know that that's just in the x-like direction?
So remember we had all agreed that vertically the center, because it's symmetrical, like if you, do you agree that it's symmetrical about the?
Yeah, but like how would you know? Like if it wasn't?
Then you'd have to repeat the process vertically. So like if the missing chunk was up here in the corner, then you'd have to do the process once horizontally and once vertically.
Okay.
Does that make sense or no?
I
No?
mean, I feel like it's the same thing.
Yeah, it's the same thing. Yeah, exactly.
Okay. Yeah.
You sure?
Sure. That's fine. That's good.
Okay. All right. Carly, you wanted me to scroll down? Here.
Mr. Hacker, do you
Yeah.
ever see the cube structure at U of M, like the architecture students made, where like
Where it
in the wind
spins.
it spins?
Yeah.
I like that.
I do too.
It reminds me
It's
of
cool.
this.
Okay. Are we good or no? All right. So I'll be honest, you guys. This probably won't come up again. That's why I was going to skip it initially. Really, the addition method seems to be applicable most often. Okay. So. All right. Everybody good? All right. Oh, and Peter, I still owe you a hug. So. All right.
Wait, it's on TV. It's on video. It's on the video.
That hug was audioly recorded.
Audio recorded.
Audioly. All right. Yeah. And then Mr. Hecker was gone. All right. Okay. All right. Now, so all of the examples that we've done so far have had uniform density. Yeah.
Can I just copy down the notes from, because we got
Yeah, I think you copied it wrong.
I'm glad that you remember.
Negative.
Okay.
Good?
Thank you. Yes.
Okay. All right. So all of the examples we've done so far have been for objects that have had uniform density, right? Like the first example we talked about was the meter stick, right? Okay, so this meter stick has uniform density. In other words, if you were to chop it up into 100 1-centimeter chunks, the mass of each chunk would be the same, right? Okay? So what happens if the density is not uniform? Okay? So this can get crazy complicated, all right? For the purposes of the AP test, what you guys are expected to know how to do is deal with a linear shape, like this is more or less a straight line, right? Okay, like the dimensions up and down and forwards and backwards are nowhere nearly as important as the length of it this way, right?
Correct.
Okay, so let's suppose that this thing was made out of a substance that got increasingly dense as we went down the length of it. Okay, so like this end had a density of 0, and then it got increasingly more and more dense. So, maybe it's styrofoam, and then cork, and then wood, and then, heavy metal, and then heavier metal, and then right down the length. Okay? So, in that circumstance, what we do is we talk about what's called linear density. Okay? So the linear density is the mass per unit length. Okay? And so we can write an expression that describes that linear density. Okay? So the Greek letter lambda is the symbol that is usually used for linear density. All right? And it's simply the mass per unit length. Okay? So the units would be kilograms per meter. Follow? So does that... All right, so that's what linear density is. So in the situation I just described, we had a thing where I said, all right, let's suppose that it gets more and more dense as you go along the length. So the way these problems will be set up is you'll be given an expression for the linear density. So on the one on this sheet, there's our expression. So the idea is, at the 0 end, our density would be 0. Okay? At the 10 centimeter mark, our density would be 0.08, etc., right? So it's getting more and more dense as you go along the length. Does that make sense? All right, so let's suppose that this meter stick matched that condition, and let's find the center of mass. All right, doing so requires a little bit of calculus and one super secret ninja trick. All right, and the first time you see this, you're gonna be like, but then it's the same thing every time. Okay. I debated waiting on this, but later on we're gonna have to learn how to calculate the rotational inertias. Do you guys remember that on the back of the toolbox sheet? We got to learn how to calculate those using calculus. And it's very similar to this process. So I think seeing it now, trying it once or twice, and then we'll revisit that kind of that same calculus trick when we get to center rotational inertia. Follow?
Yeah.
All right, so here's the calculus-y equation that you use to find the center of mass of an object. Okay? So to be clear, I want you guys to understand, remember, when you integrate, really what you're doing is you're adding up a whole bunch of little areas, right? So if you think of, I inserted a whole bunch of blank pages the other day. So here's the equation we've been using, right? We've been adding up mass times position, right? Okay? So if you think of mass as your horizontal axis and position is your vertical axis, then each of these represents a little area, right? Follow? Okay? So, but again, this is just assuming that, we've got a finite number of point particles. Whereas here we've got not an infinite, but virtually an infinite number of particles, right? That we'd be trying to, sum together. So we do that by using an integral. Okay? So this expression here, this integral, is the calculus equivalent of this finite sum. Cool? So what do you think the capital M stands for? The total mass. The total mass of the thing you're trying to find the center of mass of. Okay? So weirdly, it turns out that that mass, we got to calculate it. All right? So there are going to be two obstacles here to solve this thing. All right, so here we go. All right, so here's our deal. Can I erase? I guess there's nothing here that's... Yeah. Okay, so here we go. So to solve this thing, we need to take two integrals. Hooray, I know. All right, so let's deal with the top integral first. I'll do that in red. So what we want to do is we want to find the integral of our position with respect to mass. Okay, so what does that mean? So here's what we're going to do. So here's where the trick comes in. So we know that our density is 0.8 times x, right? And remember, oh, yeah. Oh, yeah. No, you're okay, I understand. Okay, so remember, you guys, linear density is, by definition, the mass per unit length, right? Okay, so linear density is, by definition, your change in mass per unit length. So here's the calculus trick we're going to do. So our problem is we're trying to integrate x with respect to mass, but we don't have an expression for x in terms of mass. Okay, so what I'm going to do is I'm going to rearrange this thing and I'm going to solve for dm. So if I multiply both sides by dx, you get lambda dx equals dm. All right, so some of you are going, there's no way I would have figured that out. You don't need to, because it's going to be the same exact thing every time you do one of these. Okay, so just remember, when you're doing these center of mass problems, you rewrite your dm as lambda dx. Follow? Everybody okay? All right, so now what I'm going to do is I can now literally replace dm with lambda dx. Okay, so this becomes the integral of x times lambda dx. So, equals. Cool? All right, and what's lambda? Lambda is 0.8x. So now I've got the integral of x times lambda
Excuse me.
what?
No, that's just crazy.
All right, did you follow, Peter?
Yeah, no, it's crazy.
Okay, so this is a fairly common trick. We're going to use it again when we get to rotational inertia later on. Okay, so we'll do it once or twice this chapter, and then we'll hit it again when we get to angular motion. All right, any problems? All right, so now we just got to go through and do the calculus, which actually turns out not to be that bad. So this is the integral of, let's see, x times 0.8x is just 0.8x squared dx. All right, now dx, so that means we need to integrate across the length of the thing. All right, so with my meter stick it would be 1 meter. I'm realizing though that we're dealing with a rod that's 1.5 meters long. So I'm going to integrate between a position of 0 and 1.5 meters, because that's how long the thing is. Okay? Yeah?
Sorry, so I'm very confused. So if you take the integral of x, for example, so with respect to x, and then multiply it by x, is it the same thing as the integral of x squared?
Yes.
Okay, so
Wait, say that again?
so how can you just take the 0.8x and multiply it by the integral of x?
We're not. This whole thing is it's the integral of this.
Oh,
So it's the integral of this. It's the integral of this. So all of that stuff is in the integral.
okay. That makes sense.
Good?
Yeah.
Okay. All right. So, so what did we decide were the bounds of our integration then? X is going from 0 up to 1.5 meters, right? Cool? So, integral. Well, so, figure out the integral real quick.
Oh, no, I'm tripping. Okay,
No, I think that was right, Seba.
it is 0.9.
Yeah. When I said figure out the integral, I meant do the integration. So you're going to get 0.8 over 3 times x cubed, right?
Yes.
Evaluated between 0 and 1.5. So the 0 doesn't matter, so you plug in the 1.5, and it gives you 0.9. Cool? And the units there are, well, it's x times m, so it's kilogram meters. All right, so that's that. So we're halfway done. Any problems there? All right, there's one of these on your homework assignment. It's almost the exact same thing. All right, so it's just about learning the process. If there's one of these on the AP test, it'll be just like this. It should be, yes. All right, I haven't seen it super often. The rotational inertia one seems to be more common. But, all right, everybody good?
Yes.
All right, so now, let's go back up. So now we need to deal with this bottom part. We got to figure out a way to find m. Which usually it's like, we'll just throw the thing on a scale. But we can't do that because it's a rod with this density and it's this long, and we got to find a way to find the mass. All right, so another calc trick. All right, so the question is, what's the mass? So that's a capital M. So, super secret ninja trick. It turns out that the mass is the same thing as the integral of 1 with respect to mass between 0 and m. You don't need the 1. I'm just putting it in there to emphasize something. All right? So some of you are like, what? All right, so what's the integral of 1, you guys?
X.
X, well, but in this case it's not x, it's m, right?
So max.
Okay? So don't write this down, but just listen for a second. Look what I would get. So when I integrate this, the integral of 1 with respect to m is lowercase letter m, and then I want to evaluate it between 0 and m. So you're just going to get m minus 0, and it gives you m. Did that make any sense?
Yes.
All right? Follow?
Yeah.
So, but the problem is, we don't know what m is, so that doesn't help us at all. So what we're going to do is we're going to do the same trick we used over here. This process that I used here, where I changed my dm to dx, is called a change of variables in calculus. So we're going to use that exact same trick. I'm going to replace my dm with lambda dx. Okay, so it's literally the exact same trick. So dm is just going to become lambda dx. So this is now the integral of lambda dx. And what should x run from? How long is the meter stick, you guys? It's not a meter stick. How long is the rod? 0 to 1.5, right? How long is the meter stick? 1 meter. All right. All right, and then what's lambda, you guys? 0.8x. So now we've got the integral from 0 to 1. Oops. 0 to 1. Oh my glob. 0 to 1.5. Lambda was 0.8x dx. And again, Patrick, to be clear, you're integrating this whole thing. Follow, you guys? Peter?
So
This is where the wizard hats come in, you guys.
So, like, how did we get from integrating from 0 to m to 0 to 1.5? Like,
Because
I feel like I kind of
lost you there.
lost.
All right. So the idea is, when you integrate with respect to mass, you're starting at a mass of 0 and then working your way across it until you've accumulated the mass of the whole thing.
Okay.
Does that make sense?
Yeah, it does.
So if we then change our variables and say, all right, well, we need to integrate across this whole thing, but we don't want to integrate across the mass, we want to integrate across x, what x do you have to get to before you get to the whole mass?
Okay.
Follow?
Yep.
Very good question. Follow, you guys?
Yes.
All right. Well, so we've done the hard part. Plural. All right, so now we integrate this. The integral of 0.8x, well, that's 0.8 over 2x squared. We want to integrate between 0 and 1.5. Follow? And by a weird coincidence, it turns out to be 0.9 again. And this time it's kilograms. And that's just a freakish coincidence that those both turned out to be 0.9. I should rewrite the example so that doesn't happen. Cool? All right, so look. Now we've got both of these integrals. What was the top part? What was the red? 0.9. What's the bottom part? 0.9. So my final answer then is 1. That was a lot of work to get 1, right?
I literally hate when you have like really hard problems and then it just ends up being 1 or 0. It makes me so angry. Just like, I could have just like guessed that.
I like it better than when it's like 0.5719.
No, we'll take the math.
Like, that's so annoying. It's like it's so nice when it's just like a whole number.
If it's like 11, then I'm like, yes. But like 1, if it's 1 or
I'll
0,
take 1 over.
All right. So you guys, the way these problems will be set up is pretty straightforward. Your linear density, in this one, our linear density was 0.8x. So your linear density is always going to look like this. The only thing that they might change is this exponent. Like it might be 0.8x squared, which is I think the one that's on the homework. Or it might be cubed or whatever.
52.
But exactly. But otherwise the process is exactly the same. Okay? So there's one on your homework. I feel like it's the first one on the second page. So anyway, try it. It's this exact same process. All right?
Mr. Hacker,
Yeah.
did I do like something very similar to this last year with just setting the torque at the fulcrum like equal to 0 and raising the fulcrum?
We did do that. I don't see where the parallel is. Okay, yeah, Adam.
So, like the equation that it gave us for this problem, like the x center of mass is equal to the integral x dm over
Yep.
m, is that like equivalent over every problem?
Yes.
Okay.
Yeah, anytime you're trying to find the x position of the center of mass. That's how you always do it.
Okay.
Good?
Yeah.
All right, everybody good? All right, so the next thing we need to talk about is, so Newton's second law. So Newton's second law says that the acceleration of an object is equal to the net force divided by the mass. Okay? So it turns out that that applies for a system of particles too. Okay? So, suppose we've got, I don't know, whatever, 2 or 3 particles in space, and they're all, whatever, affected by forces. Okay? You can calculate the net force on that system. And when I say the net force, I mean find the forces that come from outside the system. Okay? Divide it by the mass of the system, and that'll give you the acceleration of the center of mass of the system. Okay? So, in English, what the bleep does all of that mean? So, where did I put it? I don't like the order these slides are in. Here we go. All right, so I'm going to jump ahead a couple pages. So, flip ahead to this for me.
Mr. Hecker, I have one more quick question.
Yeah, shoot, please.
So about that equation, couldn't we just like rewrite it as like a shortcut, make it like x lambda dx?
Totally.
All right.
Yes. Yeah, and if that helps you, yeah, great, that totally works.
It's like a quick like shortcut.
Right.
So-
Yeah, so the only reason I would hesitate on that is, and actually it might be a moot point, so if you look at the equation sheet you're given, you know, on the day of the test, the only equation it gives you regarding center of mass is, duck, or pom-pom thing. The only equation it gives you is this top one. Do you know what I mean? And so and maybe it's just because I've got more math experience than you guys. For me, it's an easy jump to go from this to this.
Yeah, me too.
Like in terms of memorizing it? No.
Yeah, pretty sure.
Do you know what I mean? So I don't know. I guess if you're memorizing it anyway, then I guess, yeah, you might as well. So if you missed it, what Adam just said is, why don't we, instead of memorizing this equation, why not memorize that one? Because it's the same thing. So if you want to write that down, great. By all means. Here, let me. Oh, here, let me make my lambdas look more lambda E.
My entire childhood was just counting for lambdas.
Here. The ones with the blue dots are lambdas. All right, follow? Sorry, I know I'm jumping around a little bit. No, they would be the same because you're always integrating from your starting position to your ending position. So in the example we just did, from 0 to 1.5. So if you wanted to put your, well, it won't always be 0. So I'm hesitant to write anything there. But yes, they are the same. They're both 0 to 1.5 in that example we just did. Okay, everybody good? Carly, good? Okay, so, sorry, I know I'm jumping around a lot. So let's jump ahead to, I think it's the last page before the next chunk of notes. Is that right?
Yeah, that's what you were on.
There we go. Okay, so, jump ahead to here. All right, so everything we just talked about was about how to calculate the center of mass of an object, right? Okay, and obviously we could rewrite this in terms of, integrals, but that's basically the gist of it, right? So it turns out if you differentiate with respect to time, it gives you this equation. So if you want to find the velocity of your center of mass, it's the exact same weighted average that you did to find the position of your center of mass. So if I've got, 2 or 3 particles floating in space, and they're moving with some velocity, I can find the velocity of the center of mass just by doing that same weighted average. You just replace all of your x's with v's. Follow?
And you have, okay.
Good? Similarly, I think I said it right, you can also find the acceleration of the center of mass by using the exact same process. All right, and I'll be honest with you guys, any example that I can give you for this is going to be super contrived and dumb. And I'm going to give you exactly an example like that that's super contrived and dumb. And every problem that I've ever seen on the AP test that deals with any of these is super contrived and dumb. All right, so here's what I mean. They're going to give you 2 objects, and they're going to say, find the velocity of the center of mass. Or 2 objects and find the acceleration of the center of mass. Okay? Honestly, outside of this section, I can't think of a time when I ever would have used this to solve something. All right? It will, when we get to momentum on Monday, probably, hopefully, it will maybe shed a little bit of light as to how conservation of momentum works. But outside of that, it doesn't serve a ton of practical purpose, and it's kind of one of those things that we got to do because it's in their curriculum, and there could be a question on it. All right? So here's the dumb and contrived example. All right? So we've got an automobile, which I'm going to call a car. You guys okay with that? Car. This car. All right? So this car, here are the things I know about the car. I know that it has a mass of 1,000 kilograms. I know that it is at rest, which means that the velocity of the car initially is 0. At the instant the light turns green, the automobile starts to move with a constant acceleration. So the acceleration of the car is 4 meters per second squared. Cool? So that's all the information I know about my car. Gotcha. Okay. All right, everybody good up to there? All right, similarly, the truck, here's what I know about the truck. It's got a mass of 2,000 kilograms. It is traveling at a constant speed of 8 meters a second. So the velocity of the truck, initially, is 8 meters a second, and the acceleration of the truck is 0. So the question wants to know, how far is the center of mass of the automobile truck system from the traffic light at t equals 3 seconds? So I guess it's probably worth jotting down that they have the same starting position. So the position of the car initially is 0. The position of the truck initially is 0. Good? All right. So the idea is there's sort of 2 instants in time, right? There's the truck passing the car, right? That's when it starts. All right. And then as time goes on, the truck keeps going, the car speeds up. After 3 seconds, the car is going to be somewhere, the truck is going to be somewhere. We want to know how far the center of mass of that system has moved. Okay? Why you would want to do that? I don't know. So there's 2 ways you can do this. Option 1, figure out how far the car moves. Figure out how far the truck moves, and calculate your new center of mass. Okay? Which totally works. And to be 100% honest, if I wasn't trying to teach you guys a new thing, is probably how I would do this. All right? But instead, here's what we're going to do. We are going to calculate, so what's the position of the center of mass initially going to be, you guys? In other words, this is 0, right? Both objects at time 0 are at a position of 0, so the center of mass is going to be a position of 0, yes?
Yep.
All right, let's find the initial velocity of the center of mass. So the velocity of the center of mass initially is, so you just do that weighted average thing, right? So I'm going to do So I guess I'll write out the equation. So it's the mass of the car times the velocity of the car initially, plus the mass of the truck times the velocity of the truck initially, over the mass of the car plus the mass of the truck. Follow? So all I'm doing is I'm doing a weighted average of these two velocities. Okay? So let's see, mass of the car is 1,000. Velocity of the car initially is 0, right? Mass of the truck is 2,000. Velocity of the truck initially is 8. Over 1,000 plus 2,000. So it gives you 5.33 meters a second. Does that make any sense, you guys? I know this is really abstract, and unfortunately, there's not really an easy way to give you a visual on this.
Let's just go out in the parking lot, drive trucks and cars.
We could do that, but we'd have to find a way to mark the center of mass of the two objects as it went through space. So,
Duct tape on the car.
Yeah. From the side.
all right, are we good?
What if we got like a particle, right?
All right, is everybody good? All right, now I'm going to do the exact same thing for the acceleration of the center of mass. So the acceleration of the center of mass is, well, it's the acceleration of the car times the mass of the car plus the acceleration of the truck times the mass of the truck over the mass of the car plus the mass of the truck. So the acceleration of the car was, is it 4?
Yep.
Thank you.
Yep.
So 4 times the mass of the car is 1,000, plus the acceleration of the truck is 0, the mass of the truck is 2,000, all divided by 1,000 plus 2,000. So solve it, and you get, what, a third of 4, so 1.3 meters a second squared. Thank you. I spent all morning working on it.
Wait.
Oh, never mind.
I was
thought
just
I could've
thinking
tried
that.
Oh, it does a little bit.
What?
Apple squared.
This record, you want to fly with. Is this
Oh.
representation?
All right, everybody good? All right, so here's what we know then. So we know that the position of our center of mass initially was 0. We know the we know the velocity. We know the velocity of the center of mass initially was 5.3 meters a second. We know the acceleration of the center of mass is 1.3 meters a second. And what are we trying to find? Oh, we know the time is 3 seconds.
The center of mass, how far is it on the light at 3 seconds?
All right, so I guess, does everybody, this is a really abstract thing. I mean, do you understand that we've got these two objects moving down the road, right? Somewhere between the two objects is their center of mass, right? But the problem is they're moving relative to each other, so as they're moving, the center of mass is moving, and the position relative to the two things is changing, right? Because they're moving farther apart or closer together or whatever, right? So as the cars are moving, you've got this point in space. That's what all of this is. This is about some random point in, not random, but some point in space between the two objects moving. Follow? Okay, so what was question A?
How far?
How far is the center of mass? So how far does it move? So what am I looking for in English? Displacement. So displacement is 1/2 AT squared plus VIT. And plug in your numbers. So what are we going to get? You get half of 1.3 times 3, don't forget to square it, plus the initial velocity of 5.3 times 3. So you're going to get 16 and some other number that I can't figure out in my head. So 4 times 3 is 12, divided by 2 is 6, so 22. Is that right?
Yeah, it's 22.
Close.
What?
All right. Follow you guys? All right, and the next question says, what's the velocity of center of mass? So now you just do VF equals VI plus AT. So our initial velocity was 5.3, our acceleration is 1.3, the time is 3, so you're going to get 9.3. Those problems suck. I wish I could solve them better. I wish I could make them more interesting. They just aren't. It's what it is. Problems?
Brendan just said the greatest thing ever.
Which was?
He turned to McKeever and he goes, you could use an entire notebook to solve this problem.
All right, are we good with this?
Yeah.
All right, so next week on Monday, we're going to start learning about impulse and momentum, and then the next chunk is conservation of momentum. This is a pretty short chapter. So we'll probably have another test sometime before February break, so just a heads up. Just out of curiosity, how many of you are